So today it's my pleasure to introduce you to the QC Profiling plugin for Mgears, which enables semi-automatic interpretation of small molecule DNA conjugates or other macromolecules in a range of 6,000 to about 10,000 Dalton. This is, of course, just a short insight into the software, so I won't go through every single setting and button of the software, but I will be happy to answer any of your questions at the end of the presentation as good as I can. But first of all, why do we need this? So in our lab, with around 6 lab associates, we analyze more than 40,000 LCMS traces per year. Historically, we used to interpret them one by one using the building software of our TOF. And the results of all this analysis were then manually entered into an enormous Excel file, which was subsequently uploaded into our internal database. We were facing extremely long loading times, limiting us to a max of, let's say, 12 samples loaded at the same time. And this was leading to a very, very slow PC. So once loaded, we had to manually check and deconvolute every single peak and match them with the masses displayed in the Excel file. As you can imagine, this was extremely slow and was leading to an interpretation rate of a max of 200 traces per day in Scientist, which is already a lot. And of course, every colleague had his own interpretation style, and this led to different data coming from the same results, making the whole somehow inconsistent. Beside this, well, do I need to tell you how mentally strenuous this task was? I don't even talk about the potential of human error we have here. But now, without further ado, we come to our solution. Mgears QC Profiling. So don't worry about the size of the image. As you can see, the software is made for big screens. Or let's say it helps to have a big screen. You can actually organize all the single windows how it best fits for you. Now, by uploading the raw data and an input file, including all the wanted molecular weights and their positions in a plate, Mgears processes all the data, giving directly this image you can see here. And the plugin works perfectly with any plate format, such as 96 wells or like here, 384. But before coming to this point, you actually need to go through a few settings, of course. So Mgears allows you to customize your input file. For instance, by giving the option to define things like where is your sample identifier, or which column defines the position in the plate, or do you have smiles of SS compounds? In this window, it's also where you define where to find the raw data over here, as well as your input mapping file, where you provide sample IDs and product molecular weights down here. You can also define things like which range of the chromatogram do you want to integrate, in the first window here. Then you can also help Mgears to understand which peaks correspond to small molecular weight impurities and can therefore just be ignored. In the next window, so over here. So in the next window, you also have a set of alerts, and here it allows you to set different thresholds, like for the purity, the MS purity of different peaks, as well as starting from which threshold you recognize an unknown mass, or starting from which threshold you recognize a low molecular weight impurity, as well as samples where you just don't have any data in there. this helps you to fine-tune for which wells you want to see a warning, because human revision is really needed, and which ones can just be accepted as they are, and human interaction would be nothing else than a waste of time. On the last little window here, you can define how your input file looks like, and what information your output file should contain. The trick here in all these settings is that you can save at this point all the just mentioned settings and do the same for all different applications you might have. For example, if the configuration of your input file changes, then you just save it under another name. Then every time you need to perform a certain application, you just need to reload the corresponding setting file by clicking on the button over here, and you know it will work. So once you're happy with the settings, you select the output directory and press on process. Then after about 15 minutes to 1 hour of processing, depending on the number of samples you have, as well as their complexity, and of course the speed of your network plays also a crucial role here. We come to the point I've just shown you a few slides ago, which is this one. So here there is one important thing to understand. So the color you see in this plate doesn't give you any information about the yield or conversion of the reaction. It actually only highlights the wells asking for human interaction. So for all the white wells, the attributions are clear, and there is no need to further human intervention, meaning a perfect plate would just be white everywhere. And to treat actually the colored samples, so the samples you want to check, Mnova includes a full bunch of functionalities. As, for example, the set of alerts I just mentioned. By the way, all these colors are customable, so I choose these colors. And here in this case, we have like here or here in brown, small molecule impurities, where we assume that those will just disappear by using standard macromolecule purification methods as, for instance, ultrafiltration or SEC or gel. The gray ones are just samples containing peaks over a certain threshold with a molecular weight which is just not marked in the input file, so an unexpected byproduct, for example. And here the yellow ones, this stands for impure peaks, meaning that the MS purity of this peak is below a certain selected threshold. So you select that at the beginning in the setting file. Then we have also one additional threshold, which is not displayed here, is the red one. It's more or less the same as the yellow one, but with an additional threshold. So you can put a higher threshold, let's say. Then the initial processing also includes the integration of all peaks in a selected range, as well as their attribution according to the provided molecular weights. Nevertheless, by clicking on the corresponding well, you have the option to manually reintegrate any peak using the standard Mnova integration tools or reassign them. For this, you have helping tools such as the display of the preloaded smiles here on the right bottom, a listing of molecular weights corresponding to exactly this sample here on the left, and a manual deconvolution tool here on the top. This one allows you to deconvolute any spectrum range by just simply selecting in the chromatogram the range you want to look at, and it displays the corresponding deconvoluted mass. And of course, there is also a manual attribution button, which is this one, which allows you to assign the peak to a peak group, such as final product, for example, and then add a free text comment to it. Any of these manual modifications can then just be updated directly from the Mgears interface into the output CSV file by clicking on Analyze Again. So the just mentioned output file includes information like area %, which gives you information about the conversion of the reaction, or the remaining amount of starting material, for instance. But it also includes automatically or manually generated comments, giving information of the exact identity of these peaks. Additionally, it automatically extracts the retention times of the peaks as selected in the initial settings. This information can then be used for purification purposes, for instance, and also the area of these peaks. And this would somehow path the way to a semi-automatic quantification of samples. And this is how such an output file can actually look like. So in this example, we can find, beside the sample identifiers here on the left, the concatenated area % of, in this case, 4 different products. So here, 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 and here. And just next to it, the corresponding comment fields. And this can be either automatically generated or manually entered by reattribution. On the right side, or here, we found, in this case, the retention time of product 1. You can also choose to display more than just the first one. And on the last column here, you have also the area of the same product. All this data is automatically generated, what makes it very reproducible, nearly free of human error, and is delivered in a machine learnable format. But as said, this is just an example on how it can look like. So both the input file as well as the output files are totally customizable, and I'm pretty sure the programmers from Master Labs can help you to integrate the sort of in and output files that best fits to your needs. So in a nutshell, the here presented plugin saves a lot of time, is flexible, and ensures reproducible and machine learnable data. And all this by keeping full flexibility in the choice of the in and output files, but also helping you to focus on the samples that really need your intervention due to impurities such as small molecule impurities or unknown peaks, for example. The possibility to directly interact with the output file in the Mgears platform and exporting all needed data in a database viable format minimizes the manual handling of Excel files, further reducing the danger of human error. And at this point, I would actually like to thank the Master Lab developer team, some of them in the call, for the great collaboration, support, and most of all, patience over the last years, as well as a big thank to my lab colleagues, which heavily tested the tool to fish out every single bug and helping me to improve the software up to the great level you just could see here. And of course, thank you all for listening. With this, I'm open to any question you might have.
Thank you, Roberto. Fantastic presentation. It's nice to see Mnova Gears plugins get good use in the pharma world. Before the Q&A session starts, just a couple of things from me. First, my colleague, Maestre, software developer at Mestre Lab, will kindly help handling your questions together with Roberto. And second, you should receive an email from us with a recorded session, probably with a PDF with the slides too, I guess within the next couple of days or so. Okay, I think we have some questions. So please, Mitch, you can start the Q&A session while I display a quick poll on the screen. It would be very helpful for us if all of you could take a few seconds to answering. All yours, Mitch.
Hi, Roberto. Sorry, I was mute. So I'm starting with the questions now. The first question is, how big was the increase in productivity?
The increase in productivity, so, well, it's hard to say, but I would say, as said, we were analyzing, so the amount of LCMSs we actually produce is more or less the same, right? So what changes is the time you spend in interpreting them. Meaning, as we were making maximum 200 different traces per day per scientist, now we can even make 2 full 484 well plates, 384 well plates in 1 day per scientist, and this with really much less effort actually, and having data that is really much more reproducible than we had before.
Thank you. I think this one is similar. So what's the biggest batch of data you have run in your facility?
The biggest batch of data. So at once we actually run just 1 plate. So at once in Mnova we run 384 samples. But of course we sometimes perform kind of 10 different 96 well plates, and so we process one after the other. And as we have several licenses for this, we sometimes even do it in parallel. And while one is processing, we are just treating the other plate.
Thank you. Another one here. How does the software identify non-DNA peaks?
Well, this is tricky. This is very tricky. So our TOF is actually screening in a certain range of mass, meaning we screen something around I don't even remember, but I think 400 to 1,200. That means that small molecular weight impurities don't really ionize in this range. And that means as well, by comparing the UV chromatogram and the tick, actually, you can just identify if there is one peak in UV which is big, which you can't find in the mass. And if this is the case, then the probability that this is a small molecular weight impurity is quite high.
Yeah, thank you. There's another one. Could you please comment on the possibilities of the spectra deconvolution tool? Is it possible to deconvolute non-resolved isotope envelopes from a SQ?
Hard to answer that question. I don't know. So we have one system, and that's the only thing we actually tested. So we have several setting options in the tool, meaning that you can select a certain range of charges as well as a certain range of Dalton that you want to look at. But I don't really know if you use another sort of system, what would happen. I think the you developers of Mestre Labs should just try it and see if this works.
Okay, thank you. Yeah, I think yeah, we that's the future. We will continue growing on our capabilities in that direction. That I can answer myself. Well, what's the sample concentration in the vial and volume injection? So this is very technical question. I don't know if it's suited.
I can't really recall the sample concentration we have. So as we are moving around mostly 8,000 Dalton, we have kind of 1 nanomole per 150 microliters. I guess you will need to to calculate it by your own.
Okay, another one here. How long? No, sorry. So here is one. The in and output file seems complex. How long it took you to learn and set up the processing of your data? So let's say the learning curve for the input definition, I guess.
I'm not sure if I understand the question correctly. So yes, it is complex, but it was really complex at the beginning as we did it manually. But now, as we are automatically generating with some internal tools the input files, so no need to interact manually with it. And Nova is just giving directly a database viable output file. It is not complex at all. So I just showed you how it could look like, but we are actually not really looking at manually. So we are just taking this file and uploading it into our database.
Okay, thank you. Here is another one. A chromatogram traces a line previous to the QC profiling analysis, or I guess, yeah, during the
yeah, the tool aligns everything already. So the tool itself. Yeah.
And another one, I think this can be the last one. Do you think that this approach is appropriate for similar tasks?
I don't get the question.
Appropriate. I guess whether, let's say, whether we can apply this to a different system of different type of substract. I guess that's a.
I'm pretty sure. So our application is quite specific, and so we fine-tuned somehow to the convolution algorithm for our data. But I guess just by using different substrates and maybe different systems, you will still need to fine-tune a little bit the algorithm, or maybe the input or the settings you select for the convolution, this stuff. But I'm pretty sure that you can use it also for other applications in this size range.
Yeah, and I think I will go with thank you. I think I will go with the last one now. How long it took to develop this tool from your request to get it on your computing? Well, I think we can both answer.
Yes.
Well, but you first.
I actually do not really remember. So because our needs evolved actually during our request. So meaning that at the beginning we had an idea just to somehow make things faster and easier. But while we were doing it and while we were liking what we were seeing, we were adding more and more stuff. So I don't know, more than a year, Mitch?
Yes, I think for sure a year till, or probably
maybe nearly 2.
Yeah, bit less till we have like initial version, and then we continue improving and getting more into so being able to really fulfill all your needs. So it took some time for me to develop this, but I think it's been a really nice project.